Hello, everyone. Today I will give you a presentation on survey on deep reinforcement learning system for self-driving car. My name is Li Junwei, and here's the introduction. With the development of deep reinforcement learning, the autonomous driving technology is developing in a very good process. Some companies even made commercial success by using this system. And reinforcement learning is a very promising solution, especially in the domain of driving policy, predictive perception, path and motion planning. But why are we using reinforcement learning instead of the classical supervised learning? Well, the prediction of the agent actions changes future sensor observation, which are received from the environment. And the second one is the agent is required to learn new configuration of the environment. And so which means for the environment in the simulation, we have it has to has to be changed by our action and has to have different stage, which is exactly what reinforcement learning is. And due to emerging of deep reinforcement learning algorithm, the multiple real-world problems are addressing the area of the autonomous driving. And here is the components of autonomous driving. The first one is scene understanding. Scene understanding is basically the part that you, the perception part that have the sensors, cameras, and use this to classify the real world situation. And the second one is localization and mapping. And in this case would be the lane detection, objective detection, or something like that. The third one is planning and driving policy. So for the planning and driving policy, basically just like it said, it's how you drive. It helps you to simulate a path that is suitable for your driving. Yeah, and that's it. The fourth one is control, to accelerate, brake, steering at a certain point, or keep different speed as it needed. Methodology. So we normally use MDP to formalize the sequential decision-making process involving a single agent. And in DQN, the deep reinforcement learning system, we have 4 different methods. The first one is value-based method. We have DQN, double DQN. The second one is policy-based method, TRPO, PPO. The third one is actor-critic method, TPG, DDPG. And the fourth one is model-based, DynaQ and Dyna2. So we're mainly use value-based method and actor-critic method in the autonomous driving system. And for the value-based method, we can use it as the lane change system. And for DDPG, like actor-critic method, we normally use them in the path planning and also like the safety control system. So the deep learning algorithm for nowadays can achieve human level performance on complex tasks, such as playing a Atari game. And of course, on Atari game, they even beyond the human level performance. And in this case, I'll give you the example of DDPG, part of the deep reinforcement learning. And we can see it on the graph. This is the structure of DDPG. The policy network is used to in acceleration and steering demands. The input state parameter are partial sensor data. Then the action and state pairs are used in critics network, which is the process of Q-learning. The actor critics architecture can update the policy in the direction performance gradient. Yeah. So in this case, for the structure of all the deep reinforcement learning, no matter you are whether value-based, policy-based, or actor critics, it doesn't matter. So in the deep reinforcement learning architecture, you have to do a stochastic gradient descent. And this is very important because using the stochastic gradient descent, we are able to minimize the loss function and to get the optimal result, the optimal Q values as expected. And we are and using this method in the neural network architecture, and we can get the deep learning value. And here's an application of deep reinforcement learning. So the first one is vehicle control. Vehicle control classically has been achieved with predictive control approaches, such as model predictive control. So more recently, random search over parameter for a policy network can perform as well as linear quadratic regulator, LQR. So what is LQR? LQR is actually a dynamic programming method in the dynamic control system. And in this system, LQR are able to give the feedback of the output to the system. And for the recent work on DQN for simulated autonomous vehicle control, where different reward functions are examined to produce specific driving behavior, the agent successfully learned the turning action and navigation without crashing. Well, that's the good news. The second application is DQN for ramp merging. So it's basically using DQN and the ASTM for in the neural network to build up the system that able to let the vehicle agent to learn the automated lane change, and the result is quite impressive. The third one is IRL for driving style. So IRL is inverse reinforcement learning, and they use inverse reinforcement learning to compute the trajectory in vehicle autonomous mode and they also use DQ network as a refinement step in IRL to extract rewards. And using this method, they build up model that are able to study the individual driving style. And it performed a human level of lane change behavior. This is good. Another one is multiple goal RL for overtaking. Multiple goal reinforcement learning framework is used to solve the vehicle overtaking. In this case, this work can take correct action for overtaking while avoiding a collision and keep steady speed. Hierarchical reinforcement learning, HRL. HRL neural network policy is a network that train with semi-Markov decision process through HRL policy gradient method. The method is applied to bypass a traffic light passing test, and the test result is very good. So using HRL, you are able to the autonomous driving car are able to recognize the traffic light and do the decision by themselves. And DDPG and the safety control system. For the DLL, we can use DLL in the safety system, and for the safety system, it has to be more complex than the other policy or agent, because in this case we want because it's involving safety policy, and we want the agent be more accurate. And in one paper in 2016, DDPG and the safety-based control are combined, including artificial potential field method that is widely used for robot path planning. And using Torx as the simulation environment, the DPG is used for learning driving policy, and the policy network and the safety control are combined to avoid collision. And the result I saw on the paper is very impressive. The other one for safety is multiple agent RL for comfort driving and safety. So in this case, they use multiple agent setting, and they do they're involving the safety and the comfort of driving and trajectory planning, something like that. And the result is also very good. Validation. So here's a real world challenge and a future perspective. The first one challenge is validating RL system in real world. So so in the real world, we often have varying code bases and different hyperparameter values. This is because the real world situation is always very complex, and the environment could change drastically. And one way to solve it is in one paper, they added challenging and rare driving scenarios in high fidelity photorealistic simulators. So basically, they add more situations and more environment and more data into the system, and making the result of the safety level can increase. The other challenge is bridging and the simulation reality gap. It's quite similar with the first one. And in this case, so because the simulation are a source large cheap data with perfect annotation, and in one way to solve this problem is addressing the issue of performing imitation learning in simulation that transfer well to image from the real world. And the other way is to minimize the gap by handling the real gap during deployment of the agents in real scenario. So the second one means you actually handle the real scenarios and making them into the making the scenario into the system before you're actually putting them in the real use. And yeah, and here's the third one, sample efficiency. So the learning process requires too many samples to learn reasonable policy. This issue becomes more noticeable when collection of valuable experiments is expensive or even risky to require. And the way to solve it is reward shaping, IL bootstrapping RL, actor critics, transfer learning, meta learning, efficient state representation. The other problem is exploration issue with imitation. So in the imitation learning, and there might be a situation that your agent cannot learn all the states, and for the exploration might missing something. And the way to solve it is using data aggregation method. And the other problem is incorporating safety in DRL. We cannot deploy autonomous car in real world directly after training due to safety issues. So, and two solution we have mentioned above in the DRL and safety. And the other safety policy is safety dagger. And yeah. For the conclusion, reinforcement learning and DRL are very active area for real-world autonomous driving application. However, there's a very little literature and public data set available for us. And reinforcement learning results are usually difficult to report or reproduce and are highly sensitive to hyperparameter choices, which are often not reported in detail. The development to explicitly multi-agent reinforcement learning approaches to autonomous driving problems is also an important future challenge that has not received a lot of attention for now. And the most importantly, the deep reinforcement learning system of the autonomous car driving car, we cannot put them in the real use for a really long time, because the system is not really stable, and because the technology of classifying and simulation of all the all the possible result of the environment in the real world is limited. We do not have that much powerful machine and powerful powerful classification model to solve the problem yet. So there's still a long way to go. And here's a reference. Thank you.